Study for Unit 4, Chemical Reactions. In this unit, I will go over the difference between physical change and chemical change. I will just go over all different types of the chemical reactions really fast. Don't worry about it. We will dive deep into each type of the chemical reactions in later chapters. And then you will learn how to write the net ionic equations. And then we will do couples of the stoichiometry problems to make sure that you know how to do the math for chemistry. Let's get started. First off, chemical change versus physical changes. So a lot of procedures that occur in our real world are both physical and chemical changes. When you chop the vegetables into pieces, or when you shred the paper into couples of pieces, these are called the physical changes because the nature of the substance is not changed at all. It's still the paper. It's just paper cut in small pieces. It's still the same vegetables, just cut in small pieces. So physical change usually occurs when a substance undergoes a change in the physical forms. And then another common type of physical change is change in the phase or change in the status. So let's say the solid melts into liquid, or the liquid boils, that evaporates to become the liquid. So let's say water goes from the liquid state to its solid state, the ice. Well, this is still the water, H2O. It's written in the same chemical formula. Or water becomes the water vapor, H2O, and gas. Again, H2O has not changed. It's just changing the phase. So we call this type of change physical change. On the other hand, for chemical change, usually a new substance is formed. A new substance is created. When an apple goes through rotting, then it forms this brown surface. So on the brown surface, it's going through the oxidation, which means the brown surface, the brown color actually represents that part of the apple is different from the inner part of the apple. Or when a substance goes through combustion, when you burn a paper, then it becomes the ash. It becomes like the black powder. The ash and paper, they're two completely different substances. So it's a chemical change as well. As for the rusting, it's the same. The metal has the property of being shiny and then very malleable. On the other hand, rust is brittle. The color is different. So rust and iron, they are two different types of substance. So it's a chemical change. The same for the digestion. The food you can eat versus whatever in your intestine, they're completely different substance. So it's a chemical change. And how I actually define a chemical reaction or chemical change is it's breaking of the bonds and the formation of the bonds. So there must be some kind of bonds broken and some kinds of new bonds like formed if it's a chemical reactions. So for example, when hydrogen gas reacts with oxygen gas, then the covalent bond between the two hydrogen atoms are broken. The covalent bond between two oxygen atoms are broken, and then they form a new bonds between the hydrogen atom and the oxygen atom. So breaking of the bonds has occurred. The formation of the bonds also has occurred. So this is a typical example for the chemical reactions. Well, sometimes the breaking of the bonds also occur in a physical reaction, such as dissolving ionic compounds in water. So we know that when you dissolve the ionic compounds in water, this strong ionic bonds between the cations and anions in lattice structure of the solid ionic compound are broken, and then they are separated into separate or individual cations and anions. And then these ions are surrounded by water molecules. This is the only physical change that has breaking of the bonds involved. For all other types of breaking of the bonds, they are all considered chemical reactions. Here is a particle diagram that shows typical types of the chemical reactions. You can observe the breaking of the bonds between these two white atoms, breaking of the bonds between these two red atoms, and then new bonds between the white atom and then the red atoms is formed. For this example, breaking of the bonds between the gray and then the red atoms, and the new bonds formed between the gray and the red atoms. It's exactly the same for this one. The bond between these two atoms are broken. The new bonds between these two different atoms are formed. Sodium carbonate in aqueous reacts with 2 moles of the hydrochloric acid in aqueous to form 2 moles of the sodium chloride in aqueous states and water and the carbon dioxide in gas. A student combined 2 colorless aqueous solutions. One of the solutions contained sodium carbonate as a solute and the other contained hydrochloric acid. The chemical reactions that took place is represented by the equation above. What experimental result would be evidence that a chemical reaction took place when the solutes were combined? Usually for the chemical reactions, it's combined by some formation of the gases or the light or heat. So you can observe a couple of the evidence for the chemical change. A, bubble formed when the 2 solutions were combined. First off, bubbles are formed when there is production of the gases. Well, carbon dioxide is produced in gas, so it's possible that bubbles form. B, the total volume of the mixture is close to the sum of the initial volumes. Well, by this, I cannot really tell if the reaction has been going on or not. C, resulting solution is colorless. Again, if there is no change in the color, then you cannot really see you cannot really tell that there is evidence for the chemical reactions. D, resulting solution conducts electricity. Well, the initial solutions, the solutions also conduct electricity, so that is not a evidence for breaking of the bonds or formation of the new bonds. A beaker was half filled with freshly distilled H2O and placed in a hot plate. As the temperature of the water reached 100 Celsius degree, vigorous bubbling was observed in the beaker. The gaseous content of the bubbles were analyzed, the presence of which of the following substances would support a claim that the observed phenomenon was a physical change. Well, in this case, the bubbling is occurred, but water has just converted from the liquid state to a gaseous state. So supports the claim. The supports of which is a physical change will be the H2O and gas. So it went from H2O, water in liquid, to H2O and gas. So it's still the same substance. A chemistry teacher carried out several demonstrations and students recorded their observations. For one of the demonstrations, a student concluded that a physical change took place, but not a chemical change. Which of the following observations could the student have made of the result of the demonstration? Okay. A, 2 colorless solutions were combined and the resulting solution was pink. Okay. The change in the color, it's one of the evidence that shows that a chemical change has occurred. B, when a solid was added to a liquid, sparks was produced. Well, this is another example of the evidence that shows the change in shows the chemical change. C, one piece of solid substance was changed into small pieces. Well, of course, this is obviously a physical change. D, when 2 solutions were combined, a precipitate formed. Okay, this is also a typical evidence that shows the chemical change. Then C is the right answer. C is the only evidence that shows that this is a physical change. Next is net ionic equation. So net ionic equation is especially useful in precipitation reaction because it really shows the only reactants and the products that are actually involved in the reaction. So for example, silver nitrate, AgNO3 in aqueous reacts with hydrochloric acid, HCl, in aqueous to produce silver chloride and solid, which is a white precipitate, and HNO3, which is just a colorless, clear solution. Then if I write it in terms of the complete ionic equation, then it will be silver plus in aqueous and nitrate aqueous plus proton aqueous plus chloride aqueous. The reason I write it in terms of the ionic equation is because in aqueous state, the ionic compounds dissolve or dissociate into cations and anions completely. So this is actually how they look in the solution. They do not form a one whole ionic compound. And then for the products, silver chloride. So silver chloride is not soluble in water. So even if it's in water, even if it's in an aqueous solution, it is still in the form of this white ionic compound. And protons, aqueous, and nitrate, aqueous. So for the reactants and products, I can just easily cancel out whatever they shows up in both sides of the equation. Just like when you solve for an equation in mathematics, you always add the same number on both sides of the equation, or you subtract the same number on both sides of the equation. Okay, so protons and protons are canceled out, and nitrates is also canceled out. So eventually, for the net ionic equation, which means after you cancel out everything, you cross out everything, it will be silver cations in aqueous states react with chloride anions to yield or to produce silver chloride and solid. So the purpose of the net ionic equation is to demonstrate what's really participating in the reaction. Here is another example for net ionic equation. Potassium phosphate in aqueous reacts with magnesium chloride in aqueous to produce magnesium phosphate. And solid and potassium chloride. Then the complete ionic equation looks like this. 6 potassium cations in aqueous plus 2 phosphate anion in aqueous plus 3 magnesium cation plus 6 chloride cation to produce magnesium phosphate in solid and 6 potassium cation in aqueous state and 6 of the chloride anions in aqueous state. And now I will try to cancel out all of the spectator ions that do not really participate in the reaction. Chloride ions are canceled out. Potassium ions are canceled out. So if I rewrite this ionic equation, then it is net ionic equation, which goes by 2 of the phosphate anions in aqueous reacts with 3 of the magnesium cations in aqueous, yields or produce magnesium phosphate and solid. So this really shows the reagent, which are really participating in the reaction. And then for the potassium and then the chloride, we call them spectator ions because they are just watching this reaction. They're not actually participating. Which of the following is the correct net ionic equation of the neutralization reaction between hydrofluoric acid, HF, and the sodium hydroxide in aqueous solution? Sodium hydroxide. Well, then they yield H2O, water, and then the sodium fluoride. Then after canceling out everything, well, first off, the first step is writing it in terms of the complete ionic equation. So protons plus fluoride plus sodium plus hydroxide produce water molecule H2O and then sodium and fluoride. And then I cancel out all the spectator ions. So sodium ions and then the fluoride ions are canceled out. So eventually its protons react with hydroxide to produce H2O water molecule. The answer is C. A student combines a solution of sodium chloride in aqueous with a solution of silver nitrate in aqueous and a precipitate forms. Which of the following is a balanced net ionic equation for the formation of the precipitate? So we already went over this example. So again, the first step is to write it in terms of the complete ionic equation. Sodium cations plus the chloride anions and silver cations and nitrate anions produced the precipitate silver chloride in solid and sodium cation and nitrate anions. Again, nitrate anions and then the sodium cations are canceled out. The leftover is called the net ionic equation. So answer is A. A student combines a solution of sodium chloride in aqueous with a solution of silver nitrate in aqueous, and a precipitate forms. Which of the following is an evidence that ionic bonds form during the precipitation? A, the resulting solution is colorless. Well, it's not. It doesn't show any evidence for the chemical change. B, the resulting solution conducts electricity. Well, the reactant solution also conducts electricity, so B is not. C, precipitate has a high melting point. D, temperature of the solution did not change significantly during the precipitation. So a lot of times during the chemical change, heat is produced or light is produced, so that can be a evidence for a chemical change. But having no such a change doesn't mean that it's not a chemical change. The right answer is C. The precipitate has a high melting point, which means that the ionic bonds between between the silver and then the chlorine has formed. So ionic compound, ionic solid has high melting point, so that is why. Stoichiometry. So for the stoichiometry, we always use coefficient of the reactants and products, and it would convert them into the mole ratio to calculate all of the other related values such as mass and then the volume and concentration and etc. So for example, when carbon monoxide in gas reacts with oxygen gas to produce carbon dioxide gas, this reaction is not balanced. What I mean by that is for the reactant side, I have 3 oxygen atoms, 1 oxygen atom, 2 oxygen atom, 3 oxygen atom. On the product side, I have only 2 oxygen atoms. So I will have to do the balancing. So first off, how I do the balancing is I match the number of the elements on both sides. For the carbon, well, assuming that it's 1 carbon monoxide, then on the right-hand side, it should be 1 carbon dioxide as well. Okay, now the number of the carbon has matched, but the number of the oxygen has not matched. So to match the number of the oxygen, if I put X, then it's 1 oxygen plus X oxygen times 2 is equal to then 2 of the oxygen. So 1 plus 2x is equal to 2, which means x is equal to 1/2. So 1/2 mole of the oxygen gas reacts with 1 mole of the carbon monoxide to form or to produce 1 mole of the carbon dioxide. And a lot of times I don't like to have a fraction in the chemical reaction. So I multiply by a whole number to convert all the coefficients into the integers. Then in this case, I can multiply by 2 to convert it to a whole number 1. Then it will be 2 carbon monoxide in gas reacts with 1 oxygen gas to produce 2 carbon dioxide in gas, which means that the mole ratio of the carbon monoxide and oxygen that react with each other is 2 mole to 1 mole. So it can be 4 mole and 2 moles, it can be 6 moles to 3 moles, it can be 10 moles to 5 moles. And for example, if I am asking, okay, how many grams of carbon dioxide is produced when 30 grams of carbon monoxide reacts completely with oxygen. So the given information is gram, and now I will have to convert it into another grams. What's really important here is there is no way for us to convert between mass and mass. We can only convert between the mole ratio. We can convert between the mole ratio of the reagent and then the reactants and the products. So given the mass of the carbon monoxide, which is the reactant, then I will have to convert the mass of the carbon monoxide into number of moles of the carbon monoxide, and then convert it to the moles of the carbon dioxide, and then convert it back to the mass of the carbon dioxide. So first off, how I do the conversion between mass of the carbon monoxide and the moles of the carbon monoxide is by using the formula of mass is equal to number of moles multiplied by the molar mass. So number of moles is equal to mass divided by the molar mass. So 30 grams of the carbon monoxide is divided by its molar mass of 28 grams per mole for the carbon monoxide. Now I have the number of moles of the carbon monoxide. Now I will convert it to number of moles of the carbon dioxide. For 2 moles of the carbon monoxide, 2 moles of the carbon dioxide are produced. So I will multiply by this mole ratio of 2 mole to 2 mole. And eventually I will have to convert this to the mass of the carbon dioxide by multiplying with the molar mass of the carbon dioxide, which is 44 grams per mole of the carbon dioxide. That's it. And now let's talk about the limiting reactant versus the excess reactant. So a lot of times in the AP chemistry question, you will given only the number of moles or the mass of one of the reactants. And usually it says it reacts with excess amount of the other reactant. And then you can tell the limiting reactant is the one with a specific amount, and then the excess reactant is the other one. So for example, when carbon in solid reacts with oxygen in gas to produce carbon dioxide, the mole ratio is 1 to 1 to 1, very easy. Sometimes it's going to ask you that if 10 grams of carbon reacts with excess amount of oxygen. Then how many grams of carbon dioxide is produced? So in this situation, only the amount for one of the reactant is given, and then the amount for the other reactant is not given. But given that oxygen is in excess, which means there's abundant oxygen, so the amount for the products totally depends on the limiting reactant. For this question, I will have to do the conversion between the mass of the carbon to number of moles of the carbon to number of moles of the carbon dioxide and the mass of the carbon dioxide. So this will be 10 grams of carbon divided by its molar mass of 12 grams per mole carbon, and multiplied by the mole ratio of 1 mole of the carbon eventually produce 1 mole of the carbon dioxide. So it's 1 mole carbon dioxide over 1 mole carbon, and then multiply by molar mass of the carbon dioxide, which is 44 grams per mole carbon dioxide. A student combines a solution of sodium chloride in aqueous with a solution of silver nitrate in aqueous and a precipitate forms. Assume that 50 milliliters of 1.0 molar sodium chloride and 50 milliliters of 1.0 molar of the silver nitrate were combined. According to the balanced equation, if 50 milliliters of 2 molar sodium chloride in aqueous and 50 milliliters of the 1 molar silver nitrate were combined, the amount of precipitate form would be Okay, so if I ever write the chemical equation for sodium chloride and silver nitrate, then it is 1 mole of sodium chloride in aqueous reacts with 1 mole of silver nitrate in aqueous, and they produce 1 mole of the silver chloride in solid and 1 mole of the sodium nitrate in aqueous. So for the initial reaction, the number of moles of the sodium chloride is equal to concentration of the solution multiplied by its volume. So 50 milliliters multiplied by 1.0 molar, which is 0.05 mole. And the number of moles of the silver nitrate is also 0.05 mole. So it's balanced. The number of the mole ratio is 1 to 1, which is the same as the mole ratio of the coefficient of this reaction. But once you double the concentration of the sodium chloride, but you haven't doubled the concentration or the amount of the silver nitrate, then silver nitrate is a limiting agent, and the amount of products produced totally depends on the limiting reagent. And limiting reagent has the same number of moles as the initial reaction, so it's not doubled. There's no change. Sometimes I can combine gas law and stoichiometry to figure out the number of the moles or the volumes of one of the reactants or the products when gas is involved. For example, again, carbon in solid reacts with oxygen gas to produce carbon dioxide in gas. A lot of times it's going to give you the certain conditions such as the temperature and the pressure. We use STP the most often. STP stands for standard temperature and pressure, and then it refers to 1 atm, 1 atmospheric pressure, which is the pressure of the atmosphere that we live in every single day. And the temperature will be 0 Celsius degree or 273 Kelvin. And then at STP, what's really important is one mole of the gas. 1 mole of any of the gas at STP occupies the volume of 22.4 liters. So, for example, at STP, how many liters of oxygen gas is needed to produce, let's say, 30 grams of carbon dioxide gas? Okay, so for the liters, I can do the conversion between the number of moles of the gas and then the volume, which is measured in liters. So eventually, what is asking to convert the mass of the carbon dioxide into number of moles of the carbon dioxide. Remember, for stoichiometry, we always have to convert everything, no matter if it's volume or mass, into number of the moles, and then start doing the conversion between the moles. Conversion between different substances. From number of moles of the carbon dioxide, I convert it back to number of moles of the oxygen gas, and then I convert it back to the volume of the oxygen gas. So how I calculate it will be 30 grams of the carbon dioxide divided by 44 grams per mole of the carbon dioxide. Now I have the number of the moles, and then multiplying it by the mole ratio. So for every 1 mole of the carbon dioxide produced, 1 mole of oxygen is required. So 1 mole of the oxygen over 1 mole of the carbon dioxide, and then multiply by the conversion unit between the mole of the gas and the volume of the gas at STP, which is 22.4 liters for 1 mole of the oxygen gas at STP. Potassium sulfate in aqueous reacts with 2 moles potassium sulfide in aqueous reacts with nitric acid to produce 2 moles of the potassium nitrate in aqueous, and then sulfur dioxide gas and water in liquid. According to the balanced chemical equations above, when 100 milliliters of 0.1 molar potassium sulfide is mixed with 100 milliliters of the 0.2 molars of nitric acid at 30 Celsius degree and 1 atm, the volume of sulfur dioxide gas produced is 0.24 liters. If it is assumed that the reaction goes to completion, which of the following changes would double the volume of the sulfur dioxide produced at the same temperature and pressure, and why? Then I will have to decide which one is a limiting reactant, which one is. For this type of question, I will have to decide. For this type of reaction, I have to decide which one is a limiting reactant. The number of moles of the potassium sulfide is equal to concentration multiplied by the volume, 0.1 molar multiplied by 100 milliliters, that is equal to 0.01 mole. The number of moles of the nitric acid is equal to, again, 0.2 molar multiplied by 100 milliliters, 0.02 moles. So obviously, the potassium sulfide is the limiting reactant. Which means the amount of the product produced depends on the amount of the limiting reactant. So if I want to double the production of the product, then I will have to double the limiting reactant. So the right answer will be A, using 200 milliliters of 0.1 molar of potassium sulfide, because it then becomes the reactant in excess. Well, even if you double it, it's not going to become the reactant in excess. The amount of the two reactants balance out. B, 200 milliliters of 0.2 molar of the nitric acid. So when you double it, it's still the excess reactant. The limiting reactant is still 0.01 mole, so it's not going to double the production of the sulfur dioxide. C, using 200 milliliters of 0.1 molar of the potassium sulfide and 200 milliliters of 0.2 molar of the nitric acid, because this provides double the number of moles with a correct stoichiometric ratio. Well, that is the right answer. D, using 400 milliliters of 0.1 molar of potassium sulfide, now it's quartered, and 200 milliliters of 0.2 molar of nitric acid, now it's 0.04 moles as well, because this provides the same number of the moles of each reactant. Well, if you choose D, then the number of the amount of the products produced is 4 times bigger, so it's not D. Next is titration. So titration is a technique that's used in chemistry lab a lot, and it is used to determine the concentration of an analyte. So analyte is whatever the solution we are investigating or we're studying. And titrant is the solution that we used to determine the concentration of the analyte. So how a titration works is usually you are going to fill in the burette with your titrant, and in the flask you are going to have the analyte. You are going to carefully measure the volume of the analyte and then the volume, and then you will be given the concentration of the titrant, and then you will just drop the titrant into the flask to make sure that they react. And then after a certain period of time, when all of the analyte is reacted with titrant, so there is no analyte left over anymore in the flask, we stop this reaction, and then we call this equivalence point. And then we're going to measure the volume of the titrant used for this titration. And then we can use the stoichiometry of number of moles of the reactant 1 is equal to number of moles of reactant 2, given that these two reactants react at a ratio of 1 to 1. Then the concentration multiplied by the volume is equal to concentration of the analyte multiplied by the volume of the analyte. By then, I can calculate the concentration of the analyte by plugging in all the numbers. So equivalence point is a point at which all the analytes in the sample has reacted with titrant. A student carried out the titration using HC2H3O2 in aqueous and sodium hydroxide in aqueous. The net ionic equation for the neutralization reaction that occurs during the titration is represented above. The sodium hydroxide in aqueous was added from a burette to the HC2H3O2 aqueous in a flask. The equivalence point was reached when a total of 20 milliliters of sodium hydroxide has been added to the flask. How does the amount of HC2H3O2 in aqueous in the flask after the addition of 5 milliliters of sodium hydroxide compared to the amount of HC2H3O2 aqueous in the flask after the addition of 1.0 milliliters of sodium hydroxide? And what is the reason for the result? So it states that the equivalence point has reached when a total of 20 milliliters of the sodium hydroxide has been added. Then, which means that when you have added only the 5 milliliters of sodium hydroxide, then not all of the HC2H3O2 has been consumed. And if I compare it to the amount of the HC3H3O2 in the flask, after the addition of 1.0 milliliters of sodium hydroxide, then of course the amount of the HC3H3O2 left in the flask with 5 milliliters of the sodium hydroxide is less because it reacts with a base sodium hydroxide. Now I will give a brief overview of all types of the reactions. So depending on the rearrangement of the atoms and the reactants, I can classify the reactions into 5 different categories. One is synthesis. Synthesis occurs when 2 reactants combine together to form one reactant. So X and Y combine together to form XY. This is synthesis reaction. Decomposition means one reactant dissociates into 2 different types of the substance. So XY dissociates into X and Y. And single replacement occurs when when pure element reacts with another compound, and then it replaces one of the compounds. So X reacting with YZ, it becomes Y and XZ. So double replacement occurs when 2 compounds react with each other and then they change the position or they switch one of their compounds. So XY reacts with ZW, and then now let's say X and Z switch the position, so now it becomes ZY and XW. For combustion, it means any of the reactants, any of the substance that reacts with oxygen. This is the combustion reaction. And combustion reaction usually occurs with the carbohydrate chain in chemistry to produce carbon dioxide and water molecules. So any carbohydrate chain, carbon and then the hydrogen, they react with oxygen and then they produce carbon dioxide and water. And depending on the nature of the reaction, we can classify it into 3 different types. One is acid-base reaction. The second is the redox reaction or oxidation reduction reaction. And then the last one is precipitation reaction. So acid-base reaction occurs between 2 substances. One is acid and one is base. And then there is a transfer of the protons. Involved. For oxidation reduction reaction, it occurs between 2 of the reactants when there is a transfer of the electrons. On the other hand, for the precipitation reaction, usually how it occurs between 2 aqueous solutions. And then a new ionic bonds form between one of the substance in each of the aqueous solution. And then it forms an insoluble solid in the aqueous solution. Let's take a closer look at acid-base reaction. As I stated before, acid-base reaction is transfer of the protons between two species. And then how we define the acid and base is a little bit different from how we usually define acid and base in real world. In real world, we define something that tastes sour or smells sour, such as vinegar or fruits, as acid. But in AP chemistry, we use the Bronsted-Lowry model to define it. So according to Bronsted-Lowry model, acid is the proton donor. And according to Bronsted-Lowry model, the proton acceptor is base. So according to Bronsted-Lowry model, the acid might have a pH value that's greater than 7 or even equal to 7. And then the Bronsted-Lowry base might not be actual base when you measure the pH value. And once the Bronsted-Lowry acid has lost a proton, we call it conjugate base of that acid. So for example, when hydrochloric acid, HCl, reacts with water molecule, H2O, and then donate its proton to the water molecule, then it becomes chloride, Cl-, and then hydronium ions, H3O+. So obviously, the hydrochloric acid has donated a proton. So this is considered Bronsted-Lowry acid in this acid-base reaction. And once it has lost the protons, the chloride ion is called the Bronsted-Lowry base. Once it has lost the protons, we call it conjugate base of hydrochloric acid. And the water molecule H2O, it is Bronsted-Lowry base because it accepts the proton. And once it accepts the proton and becomes hydronium ion, we call it the conjugate acid of water. In the reaction, C5H5N inaqus and HCl inaqus represented above C5H5N acts as, well, let's take a look at this reaction. So hydrochloric acid became a chloride, which means it has donated its protons to C5H5N. And then the proton is attached to, is covalently bonded to the nitrogen after the reaction. So obviously there is a transfer of the protons, and this is a acid-base reaction. And hydrochloric acid, which is a proton donor, is Bronsted-Lowry acid. C6H5COOH in aqueous reacts with sodium hydroxide in aqueous to produce C6H5COONA in aqueous and water molecules in liquid. Which of the following identifies a conjugate acid-base pair in the reaction represented above? Well, now I see that the C6H5COOH, well, is the proton part is replaced with sodium, which means the proton is donated by C6H5COOH to the sodium hydroxide or to the hydroxide ions. So what's actually occurring is C6H5COOH react with hydroxide to yield C6H5COO- and H2O. So this is a Bronsted-Lowry base, and this is a conjugate acid. And this is a Bronsted-Lowry acid, this is a conjugate base. So the correct conjugate acid-base pair is not A, it's not C, not D. The right answer is B. So after losing this proton, it becomes the conjugate base, C6H5COO-. The redox reaction. Redox reaction is an abbreviation for reduction-oxidation reaction. So it does mean that two types of reaction occur at the same time. And it is defined by the transfer of the electrons between two species. So by transfer of the electrons, the oxidation number actually changes. And we can write the redox reaction into two half reactions. One is reduction and one is oxidation. So for example, copper 2+ reacts with zinc to produce copper in solid. Copper to produce copper and zinc cations. Then I can separate it into two of the half reactions. One is copper cation becomes the copper. The second one is zinc becomes the zinc cations. Well, for the half reaction, I will have to add the electrons to make sure the reactions are balanced. For the first half reaction, on the left side, I carry a charge of 2 plus, so I will have to put 2 of the electrons to balance it out. For the second reaction, I have zinc 2 plus with a charge of plus 2, so I will have to add 2 of the electrons on the right side to balance it out. Okay, and then how I define a reduction and oxidation is, reduction is gaining of electrons, and oxidation is losing electrons. So out of these two half reactions, the first one means the copper has gained electrons, so this is reduction. And then the second one, zinc dissociates into zinc 2 plus and then 2 of the electrons. So electrons are produced, so this is the oxidation reaction. And for oxidation reduction, we observe the oxidation number actually increase. And for the reduction, we will observe a decrease in the oxidation number. So how I calculate the oxidation number is by, first off, if it's a monoprotic. First off, if this is a single element and it's the form of an atom, then it has the oxidation number of 0. So for example, the zinc will have a oxidation number of 0. In zinc 2 plus, it's in the form of one single ion, so it has the oxidation number of positive 2. So the oxidation number has increased for this half reaction. Which of the following represents the oxidation half reaction based on the balanced ionic equation shown above? Again, this is an oxidation half reaction, which means either losing the electrons or increase in the oxidation number. So oxidation number has increased for iron. Iron's oxidation number has changed from positive 2 to positive 3. So I will only put the iron out of this reaction. So it is iron 2 plus converting into iron 3 plus. But this is not done yet because I have to fill in the electrons to make sure that the charges are balanced on both sides. So on the left side, I have 2 plus charge. On the right side, I have 3 plus charge. So I have to put one single electron on the right side. So 3 minus 1 is equal to 2. So B is the right answer. Based on the half reactions represented above, which of the following is the balanced ionic equation for the oxidation reduction reaction between aluminum and solid and the tin 2 plus aqueous? So now you have 2 separate half reactions and you will have to combine them together to form a full oxidation reduction reaction. So for this type of question, you just need to match the number of the electrons. For the first half reaction, I have 3 electrons on the right side. For the second half reaction, I have only 2 electrons on the left side. So how I match it is by multiplying the first half reaction by 2 and multiplying the second half reaction by 3. So it will be 2 aluminum reacts with 3 of the tin ions and then 6 of the electrons to produce 2 of the aluminum cations and 6 of the electrons and 3 of the tin. And of course, electrons get cancelled on both sides. So the leftover will be this reacts to form these 2 products. The right answer is equal to, so the right answer is option 3. So the right answer is C. The very last is precipitation reaction. So precipitation reaction occurs when you mix the solutions of two different types of solution, and then they form a insoluble ionic compound. So remember that for all the precipitation reactions, so you will have to write the net ionic equation for precipitation reaction to really make sure or to really know what is going on or which reactants are participating in the reaction. And for this, we don't have to memorize the solubility rule. We only need to memorize that all of the sodium, potassium, ammonium, and nitrate salts are soluble in water. So if I ever mix the sodium chloride in aqueous with potassium nitrate in aqueous, then this reaction does not form any of the precipitates because any of the salts with like potassium and nitrates and then the sodium involved are soluble in water. So no precipitation, no precipitate is formed. And no reaction. Which of the following best describes the process represented above that takes place when ammonia is added to water? So ammonia reacts to water molecule, and then ammonia is converted to ammonium by accepting a proton from the water molecule. So this is a acid-base reaction because there is a transfer of the protons. The proton is exchanged from water molecule to the ammonia. When the reaction represented above proceeds, heat is produced. Which of the following best describes the reaction? A, it is a combustion reaction. It is not a combustion reaction, obviously. For combustion, oxygen has to be involved. B, it is a double replacement reaction. Double replacement reaction only occurs when it's two compounds reacting with each other, such as XY reacting with ZW. But zinc is an element, so it's not double replacement. C, it is an acid-base reaction because hydrochloric acid is an acid that is capable of exchanging protons. So the protons, if the protons has been transferred to the zinc, then it is an acid-base reaction, but it's not. So C is not the right answer. It is an oxidation reduction reaction because zinc is oxidized and hydrogen is reduced. So zinc is in the form of the element, so it has an oxidation number of 0. In zinc chloride, zinc has an oxidation number of positive 2 because the chlorine is a halogen, and then in a compound, the halogen always carry the oxidation number of -1. So 2 of the chlorine means it's 2 times -1. To balance it out, zinc must have an oxidation number of positive 2. For the hydrogen, if it's in the form of the element, then of course it carries the oxidation number of 0. And when it's combined with the chlorine, which is the halogen with an oxidation number of -1, hydrogen carries the oxidation number of +1. So for a hydrogen, its oxidation number has decreased. For the zinc, its oxidation number has increased. So it's a redox reaction. Which of the following statement about the reaction represented above is correct? 2 magnesium in solid reacts with 1 silicon tetrachloride in liquid to produce 2 of the magnesium chloride in solid and silicon in solid. A, it is an oxidation reduction reaction because magnesium is oxidized. So the oxidation number of magnesium was 0. For the reactant. For the product, it's +2. So it is oxidized, right? What about B? It is an oxidation reduction reaction and electrons are transferred from silicon tetrachloride to magnesium. Okay, so magnesium's oxidation number has increased, which means it's oxidation for the magnesium. Oxidation means it is losing electron. So the electron has transferred from magnesium to the silicon tetrachloride. So B is not correct. C, it is an oxidation reduction reaction and the oxidation number of the chlorine changed from +4 to +2. Okay, so for the chlorine, which is a halogen, it always has an oxidation number of -1, no matter if it's combined with the silicon or the magnesium. So C is not correct. D, it is not an oxidation reduction reaction because none of the oxidation number has changed. So obviously magnesium has a change in the oxidation number, so D is not right.